Hello everyone. Welcome to today's live broadcast. A new dimension in UHPLC, 1.5 millimeter ID columns for robust separations with increased sensitivity and solvent savings. I'm Laura Bush, the editorial director of LCGC, and I'll be your moderator for today's event. We're pleased to bring you this webcast presented by LCGC and sponsored by Advanced Materials Technology. Advanced Materials Technology is an innovative product development and HPLC column manufacturer focused on improving the presentation of the sample to the detector. From pioneering fused core technology in 2005, the Halo product line has changed previous conventional wisdom that high resolution requires high back pressure. Now in its 17th year, AMT continues to be a leader in novel superficially porous particle development, enabling high efficiency and reliability for scientists involved in both small and large molecule separations, and delivers application-specific solutions designed to meet specific industry challenges. Before we begin today, we have a few housekeeping announcements. First, the webcast is designed to be interactive, so we encourage you to ask questions. You can submit questions at any time by typing them in the Q&A box, and you can find that on the right-hand side of your screen. You can enlarge the slide window by clicking on the small square icon in the upper right-hand corner of your window, or by hovering your mouse over the lower right-hand corner and dragging the window to the desired size. The slides will advance automatically during the webcast. And if you have any technical problems viewing or hearing the presentation today, please click on the question mark Help widget in the dock at the bottom of your window. I would now like to introduce today's speakers. We are very pleased to be joined today by Dr. James P. Grinius and Dr. Stephanie A. Schuster. Jim Grinius is an associate professor in the Department of Chemistry and Biochemistry at Rowan University. His research focuses on liquid chromatography and microfluidics, as well as the design of low-cost and miniaturized platforms to facilitate these techniques. He is also actively involved in several leadership roles with the separation science community, including the Chromatography Forum of the Delaware Valley and the ACS Subdivision on Chromatography and Separations Chemistry. Stephanie Schuster earned her PhD under the guidance of Professor Joe P. Foley at Drexel University. She joined Advanced Materials Technology, AMT, in June of 2009 as a research scientist working with Dr. Jack Kirkland, providing contributions to the commercial development of products designed for peptide and protein separations. Most recently, as part of the technical support team at AMT, Stephanie has been providing customers support in optimizing and troubleshooting their applications. Thank you both for joining us today. Please get us started.
Thank you for that great introduction. Today we're going to be talking about a new dimension in UHPLC and discuss some various aspects of 1.5 millimeter ID columns for robust separations. I'm Jim Grinius, and Stephanie Schuster will also be speaking with us today. So just as a brief outline of today's talk, I'm going to talk a little bit at the beginning about some of the fundamental benefits that we may observe as we move to smaller ID columns, as well as some other things we might need to consider in terms of running those types of methods. Then I'm going to turn it over to Stephanie, who's going to talk a bit about the benefits of smaller IDs with 1.5 millimeter ID UHPLC columns. Then finally we'll close up with a Q&A session. So in terms of thinking about the broader scope of HPLC columns, going in the past, historically, a very common inner diameter was 4.6 millimeters, and those columns were typically operated at 1 mil per minute or higher. Eventually, there was a move to 3 millimeter ID columns as a way to save solvent. And as you think about scaling the flow rates, you would need to operate a 4.6 millimeter column of 100 millimeter length down to a 3 millimeter ID column with 100 millimeter length. You might go from 1.5 mils per minute down to 0.8 mils per minute. And so in running the same method, you would save about half of the solvent. More recently, with the move to UHPLC, there was a shift to 2.1 millimeter ID columns, and as well a transition to even lower flow rates, which also has some benefits as you interface those types of columns to mass spec. And so as we think about this transition down to smaller and smaller IDs, you see that there are diminishing effects of viscous friction. We're going to talk about those here in a minute. you see that you can actually get an increase in your signal if you inject the same sample concentration of volume. We'll talk about that a little bit. And also, as we mentioned before, you're going to have less solvent consumed, so there's reduced consumable costs as well as waste disposal costs. So there are some potential financial benefits on both sides, as well as some green analytical chemistry benefits by reducing the amount of solvent you're using. And so first I want to talk a little bit about viscous friction and what happens as we transition to these smaller internal column diameters. And so what happens in viscous friction is the formation of thermal gradients within the column. And effectively, you can think of viscous friction as something that leads to the generation of heat. And we can consider generation of heat as a power calculation. And so if you calculate the flow rate times the pressure drop across the column, that will lead to a formation of some amount of energy per unit time, which is how we record power. And so the way that this heat that's generated has to dissipate leads to actually the formation of two temperature gradients within the column. And so there's an axial temperature gradient where you actually find that the mobile phase gets warmer as you move from the inlet of the column to the outlet of the column, as well as a radial temperature gradient where the mobile phase is warmer at the center of the column and gets cooler as you move to the walls of the column. And both of these things can have some detrimental effects on our chromatography. Those axial gradients can lead to less reproducible elution or retention times, and the radial gradients can potentially lead to lower efficiencies, especially when you're under conditions of viscous friction where you might be generating powers of up to 4 watts per meter of column length and higher. And so briefly, I want to talk about each of these effects a little bit more in depth. And so first, the axial thermal gradients. So these are ones that tend to form in ideally adiabatic, but in general, within traditional experimental conditions, generally it's a quasi-adiabatic environment. And so we see those in instrument platforms where maybe we're using column insulation or a still air oven condition, no sort of convective movement from an oven fan. And so what this leads to is potentially a little bit of higher efficiency because we're not seeing some efficiency drops from the radial thermal gradients that I'll speak to in a moment. But because you have this increase in column temperature as you move from the column inlet to the column outlet, you can potentially see some shifting retention times and basically a small drop in retention from run to run, but also across the flow rate range. Now, if you wait long enough, you can reach a thermal equilibrium point, but run to run, there may be some reproducibility issues. So as you can see here on the plot on the bottom left of this slide, we have some columns where we were running a column oven where effectively we didn't do much to actually have any sort of insulation, and then a flowing water jacket, which is a condition where effectively what you're able to do is maintain the temperature as close to isothermal as possible. And as you see under the column oven condition where it is a quasi-adiabatic, but at least no movement to try and remove heat directly from the walls of the column, you see that increase the flow rate, you see a bigger drop in the retention factor for a given analyte across the range due to the increasing magnitude of the axial thermal gradient at higher and higher flow rates and the consequential higher and higher pressure drops. The same type of thing can occur in quasi-isothermal environments like the water jacket I just mentioned, or potentially an oven that uses forced air convection with a fan. And so in those cases, the bigger temperature gradient that forms is the radial one, where again, as I mentioned, you have warmer mobile phase in the center of the column, and then it gets cooler as it goes to the walls where the heat basically be escaping or removing. And what this does is this hurts the homogeneity of basically the cross face of the column, which is one of the big things that can lead to a loss in chromatographic efficiency. So if we look at a Van Deemter curve here, what you see in this case in terms of the negative effect is here the blue trace for the flowing water jacket compared to the column oven where we don't have as much of this heat removal. In that case, you can see that as we go to the higher and higher linear velocities, again, higher flow rates, higher pressure drops, in those cases we see much higher plate heights as well, so a loss in our overall chromatographic efficiency. So what we see in this case is, yes, maybe we have better run-to-run retention time reproducibility, but we are losing some efficiency. Now, under practical conditions, you're not ever able to maybe fully remove either of these effects. They both exist in most conditions where you are running at high flow rates and high pressures. But you can, again, set these various column environments to try and minimize one effect or over the other. Now, the reason this kind of affects into internal column diameter is as we think about what is the flow rate we might need to operate a given column. And so if we look at a variety of various column inner diameters from 4.6 millimeter down to 50 microns, so a very small diameter capillary column, and we think about what type of flow rate might be needed to operate that column while we may potentially maintain the pressure at the same level in all cases. So the pressure drop may stay the same over the column, but because we're going to smaller diameters, we're going to see lower flow rates. That product, the power generation of flow times delta pressure drop, will decrease significantly as we go to smaller and smaller column IDs. So at 4.6 millimeter, you might be generating enough power to boil the mobile phase before it exits the column. This was a key motivating factor moving down to 2.1 millimeter ID columns as the move to UHPLC happened, but this also provides some motivation to go to even smaller IDs below 2.1 millimeter as well, as a way of further minimizing this viscous friction effect, especially as we think about high throughput separations. Next, I want to talk a little bit about what happens to the peak signal as we move to smaller internal column diameters. So most LC detectors that are commonly used operate in a concentration-sensitive type mode. And what we can think about that in terms of a practical analysis is that the limits of detection are really improved when the LC is delivering a highly concentrated sample past the column and to the detector. And so what we want to try and do is potentially minimize the dilution in the mobile phase. And so that means we want to try and make sure our peaks are as narrow as possible, but also if we run at a lower flow rate, that will help as well. And so the flow rate optimum that we're going to run at to maintain linear velocity is going to scale with the ratio of the square of the radius of the column. And so if you want to think about that, maybe just as a move from a 4.6 millimeter ID column to a 1 millimeter ID column, if we were operating our 4.6 millimeter column at a 1 mil per minute flow rate, if we wanted to try and run the same method on a 1 millimeter ID column and keep a similar separation time, maintain that linear velocity, we would drop that flow rate down to 50 microliters per minute. And so if our bands were maintaining the same width, but our flow rate is 20 times lower, then effectively what we might see is a 20-fold enhancement in the overall peak signal. And now, one thing to keep in mind is that this calculation is based on an identical sample load, so that means we have the same injection volume and same sample concentration going into the column and eventually after separation through the detector. And so there are sometimes, you have to think about the actual injection volume you're loading onto the smaller ID columns, and gradient operation can help with some of those things. But just one thing to keep in mind as you move down to the smaller and smaller ID columns is that as you reduce that flow rate, you can see some signal enhancement. And so here, looking at some data we've collected in the lab, if we think about a column with the same length, same packing material, but moving from a 2.1 millimeter inner diameter down to a 1.5 and finally a 1 millimeter, you can see that we see an increase in the peak signal, in this case kind of tracking that third peak in the separation. And actually, the area scales pretty much perfectly as you would expect for the signal you observe with that square ratio that I discussed on the previous slide. But what you see here is we are getting that increase in signal as well. So we may be seeing a slight widening of the band. We'll talk about the reason for that in the next section. But just looking at this data clearly here, you can see that if you maintain the sample concentration and maintain the injection volume, what you're getting is a big increase in your signal as you decrease the inner diameter of the column. Now, extra column effects are the one thing we have to be careful about as we transition to these smaller ID columns. And so as we think about all the things that may lead to band broadening outside of the actual chromatographic column itself, there are things we need to worry about before the column. And some of those would be the actual sample injection volume, mechanism of that injector, as well as the volume of the pre-column tubing connecting the injector to the column inlet. As we think about beyond the column, the next thing we're going to have to consider is the connection we have from the outlet of the column to the detector, and then what types of volumes are there, either in an optical flow cell or potentially in some sort of ionization source for mass spectrometry detection. And so those volumes and how they relate specifically to the volume of the column we're working with are something we need to think about as we think about these bands broadening. And so again, the peak area signal will sort of follow that ratio exactly, but the heights are going to change relative to the widths as well, because we're maintaining the overall peak area. And so if we want to look at that here, going between a 2.1, a 1.5, and a 1, you can see that effectively we're getting slightly broader bands as we move from the blue trace, the 2.1, to the 1.5, that orange trace, to the 1, that black trace. And so we are seeing the signal increase as we would expect. The viscous friction effects are decreasing because even though the pressure drop might be comparable, we are decreasing the flow rate as we maintain that velocity. But the one thing we have to make sure that we consider is that as we go to those lower and lower inner diameters, the overall column volume is smaller, and so the extra column effects, if we don't change our tubing, but if we leave everything the same, the percentage of the volume that's extra column relative to the column itself does grow. And so that has been one thing that makes moving from 2.1 to a 1 millimeter ID column somewhat tricky. And so a 1.5 millimeter ID column is sort of a nice compromise in the middle that allows you to balance the effects of improved signal while not having to worry quite as much about the extra column effects. So with that, I'm going to turn it over to Stephanie, who's going to be able to talk a little bit about some of the various applications of the 1.5 millimeter ID columns. But again, just to summarize before we turn it over, smaller ID columns, less detrimental effects due to viscous heating, primarily because we have lower flow rates that we're operating at. Those lower flow rates also allow us to have increased signal and reduce solvent consumption. But in doing so, we must remember that we have to take into account the extra column effects and minimize those as much as possible to fully realize those benefits. And with that, I'll turn it over to Stephanie.
Thank you, Jim, for handing it off. And now I'm going to describe the applications of our new 1.5 millimeter ID column. So here you can see the new end fittings that are indicative of our 1.5 millimeter ID columns. And part of the reason why we're introducing this dimension is in order to bridge the gap between analytical and microflow. So we know that people want the advantages of capillary systems, but they don't necessarily want to do all the work that it takes to move to a capillary system, including investing in that specialized equipment and then working with capillary columns. So the 1.5 millimeter ID is meant for those people who have UHPLC systems, but they just want to get a little bit more from that particular system. So what benefits are we talking about here? Well, it's exactly the same thing that Jim has just described to you. So we're looking for more performance from UHPLC and LCMS systems. In particular, more sensitivity from conventional UHPLC systems. Higher ionization efficiencies from LCMS systems. That reduction in ID also provides solvent savings and reduced waste disposal costs, which then lead to a smaller chemical footprint. And then finally, the ease of implementation of a microflow solution. So first I'll describe some increased sensitivity from conventional UHPLC systems. Here I'm showing the comparison of over-the-counter cough and cold medicines. So in the orange trace, we're seeing the results from the 1.5 millimeter ID column compared to the blue trace, which are the results from the 2.1 millimeter ID column. The areas are an average of 2 times larger on the 1.5 millimeter ID column, which goes back to what Jim was saying in terms of the square of the ratio of a 2.1 to a 1.5 millimeter ID. And we're seeing peak heights that are an average of 1.7 times taller on the 1.5 millimeter ID column. So where this would really be a benefit is when analysts are looking at enhanced impurity identification. So in this example, the top trace is what we had run on a 3 by 100 millimeter Halo C18 column for a mix of, again, cough and cold medicines. But in particular, we're looking at peak 4 salicylic acid, which is an impurity from aspirin. So looking at the comparison of the top trace to the bottom trace, which is our result on the 1.5 millimeter ID column, you can see the area of peak 4 is 4 times larger, and the peak height in this case is more than 4 times taller for the result on the 1.5 millimeter ID column. Now, in terms of higher ionization efficiencies from LCMS systems, we looked at this example of intact trastuzumab using Halo 1000 angstrom diphenyl. So the top trace are the results from the 1.5 millimeter ID column run at 0.2 mils per minute, compared to the bottom trace, which is the result from a 2.1 millimeter ID column run at double the flow rate, 0.4 mils per minute. And what you can see is an area of 2.9 times larger, and of course the peak height is increased. We see similar effects when we look at reduced and alkylated trastuzumab, also using the Halo 1000 angstrom diphenyl. So again, the top results, this is the TIC from the 1.5 millimeter ID column, and that's compared to the bottom trace, which is showing the TIC from the 2.1 millimeter ID column. The light chain is showing an area of about 2.7 times larger compared to the 2.1, and the heavy chain area is about 2.3 times larger than the result that we're getting on the 2.1 millimeter ID column. So this is, we're showing these increases, but one thing that you have to keep in mind is when you're running at a slower flow rate, you have to also optimize your source conditions. And that's what we needed to do for this particular comparison, showing a norfentanyl and fentanyl on the 2.1 millimeter ID on the left-hand side of the slide, compared to the 1.5 millimeter ID results for norfentanyl and fentanyl. So you can see we're getting about 2.5 times gain in intensity and 2.4 times gain in area with norfentanyl on the top right-hand side trace, compared to the fentanyl signal, which is 2.6 times more in intensity compared to the 2.1 millimeter ID on the left-hand side of the slide. And again, the area is 2.4 times larger with the 1.5 millimeter ID column. These are the average of 5 injections each, and what we had done was injected 1.5 microliters of a 2 nanogram per mil sample. Next, I'd like to talk about reduced solvent consumption compared to the 2.1 millimeter ID columns. Here I'm showing the peptide map of trastuzumab with the orange results for the 1.5 millimeter ID column and the blue results for a 2.1 millimeter ID column. And on the top right-hand trace, you can see we're getting 50% solvent savings, which also translates to reduced waste disposal cost and that smaller chemical footprint. So if you can imagine running multiple peptide maps over the course of several days, that would add up to a lot of solvent savings, a lot of reduced waste disposal costs, and also you're seeing that benefit of the higher signal intensity from the smaller ID column. Now, if you were to go from a 4.6 millimeter ID column, you would see you need even greater reduction in solvent savings. So here I'm showing the example of 13 cannabinoids. Again, the orange result is from the 1.5 millimeter ID column compared to the gray trace, which was run on a 4.6 millimeter ID column. And in this particular example, we had run the 4.6 millimeter ID column at 1.5 mils per minute compared to 0.159 mils per minute for the 1.5 millimeter ID column. And in this case, we're getting 9.4 times solvent savings going from that larger 4.6 millimeter ID down to the 1.5 millimeter ID column. And you can see the signal intensity is also about 9.4 times larger with the 1.5 millimeter ID column results. Now I'd like to talk about some stability experiments that we ran with the 1.5 millimeter ID column. So what we're showing here is a Halo 1000 angstrom diphenyl, which was run for 1,000 injections at 600 bar. And you can see this has no loss in efficiency or retention over the course of this particular experiment. So just like you would expect stability from 2.1 millimeter ID columns and larger, you're seeing the same sort of performance from the 1.5 millimeter ID column. We observed the same sort of experiment in terms of a Halo 90 angstrom C18 column. It was also run at 600 bar for 1,000 injections. I'm just now plotting a trace of injection number on the x-axis versus retention factor on the y-axis, and you can see how the retention is maintained across all of those 1,000 injections. And the percent RSD is 0.28% for the retention factor. In terms of Halo 1.5 millimeter ID column reproducibility, now I'm talking about reproducibility from 3 different lots of column hardware. So what we did was we took 3 different column hardware lots and loaded them with the same lot of Halo C18 and ran the over-the-counter cough and cold medicine mix. And you can see the retention time percent RSDs were all 1% or lower. So there's really good reproducibility from this particular column hardware. And it would be reliable if you decided to incorporate it into your methods. So I've talked about the benefits of the 1.5 millimeter ID, and one of the nice things about it is that it's an easy to implement microflow solution. So in fact, the column looks and feels like a 2.1 millimeter ID column, and successful implementation requires system optimization via hardware and accessories. So what do I mean by that? In order to get the most out of the Halo 1.5 millimeter ID columns, you'll need to have a UHPLC system that has low dispersion, and in order to get the low dispersion, you'll have to optimize the connections between the injector and the column to the detector. And then, of course, you'll have to scale the flow rate in terms of if you're doing a method transfer to the 1.5 millimeter ID. So I'll step you through these in the next few slides. So in order to get the most out of the 1.5 millimeter ID columns, you have to be aware of the extra column dispersion that's present in all UHPLC systems. So here I'm showing variance charts under gradient conditions, and the reason I'm specifying gradient conditions is because when gradient methods are used, everything leading up from the sample injection volume to the pre-column tubing doesn't really impact the result that's observed, because for gradients you usually have some sort of focusing at the head of the column, which diminishes any impact from extra column dispersion effects before you get to the column. So here, Dwight Stoll, Thomas Lauer, and Ken Brockhoven had written a nice 4-part series in LCGC North America all about dispersion and extra column peak broadening. And along with that, they have this dispersion calculator that's available here at this particular website. And this is how these plots on the right-hand side of the slide were generated. So what you can see is for the upper right-hand side, the yellow wedge is the dispersion from the column. The gray wedge is dispersion from the detector, and the blue is any post-column tubing. So the idea here is, in order to get the most out of the 1.5 millimeter ID columns, you want to maximize the area of that yellow section, which corresponds to the column. And in so doing that, what that will mean is, what you'll see is taller peaks in terms of the response, and also narrower peaks in terms of the width. So in the comparison for our standard UHPLC, which had dispersion of 14 microliters squared, you can see for, in particular, peak 8, we had a height of 66 milliAU and a width of 0.046 minutes with that particular setup, compared to when we had optimized the system going to smaller ID tubing coming out of the column into the detector. The height increased to 105 milliAU and the width decreased to 0.037 minutes. So this is the kind of impact that you could see when you lower the dispersion of your UHPLC system. So there are many different manufacturers that offer different connecting tubing for use in UHPLC. AMT has partnered with IDEX, and we're offering their Marvel Exact connectors in order to help reduce extra column dispersion in the system. But the nice thing about the Marvel Exact tubing is that it has a flat sealing surface. What that means is you have zero dead volume, as shown here on the left-hand side picture, compared to a ferrule fitting, which sometimes doesn't completely bottom out and could lead to some extra internal volume. And that extra internal volume would therefore potentially lead to misshapen peaks, sometimes fronting or tailing. These are offered in both peak sill and peak line stainless steel options, and we're recommending that peak sill is used for any connections to a mass spec source. The peak line stainless steel option is good for going from sample injector to the inlet of the column. And then on our website, we're including the volume with each dimension for easy selection. And that's listed here in nanoliters. So how do you transfer a method to a 1.5 millimeter ID column? Well, it's just exactly as how Jim had described it earlier. What you want to do is scale the flow rate. So, and that scaled flow rate is really just the cross-section of the column. The ratio of that squared is how you're able to scale the flow rate. So F2 would be the new flow rate for the 1.5 millimeter ID, and F sub 1 would be your existing flow rate. So to make it easy, all you have to do is use the ratio of the diameter squared in order to calculate what would be your optimum flow rate for the 1.5 millimeter ID column. Of course, if it's a gradient method, you'll need to add an isocratic hold to account for the dwell volume. And then you can scale the injection volume to maintain the signal, or keep the same injection volume for increased signal. And that's what we've done for the results that I've talked about in this presentation. The benefits of fuse core in a 1.5 millimeter ID column are still apparent. So in this comparison, we ran the cough and cold medicines at 0.2 mils per minute with a back pressure of 268 bar, compared to doubling the flow rate and having the gradient time. The back pressure, of course, will go up, but the gradient is 2 times faster with minimal loss in resolution. And I'm pointing out the resolution between peaks 3 and 4, which went from 5.4 when we were running at 0.2 mils per minute compared to 4.3 when we ran at double the flow rate. So this increase in runtime is one of the benefits of fused core particles because of our ability to increase the flow rate and still maintain that good resolution. So the Halo 1.5 millimeter ID columns are available in 2.7 micron particle size. In particular, we have stationary phases for small molecules, our 90 angstrom C18 for peptides, the 160 angstrom ESC18, and then also for proteins. So we have the 1000 angstrom C4 and the 1000 angstrom diphenyl. And then in terms of column lengths, they're available in 50, 100, and 150 millimeter lengths. So in terms of a summary, I've shown examples of more sensitivity from conventional UHPLC systems, higher ionization efficiencies from LCMS systems, of course, reduced solvent consumption compared to 2.1 millimeter ID columns and larger, that easy-to-implement microflow solution, and of course, it's made by a trusted manufacturer of fused core columns in a 9001 ISO-certified facility. And finally, it's available in chemistries for small molecule, peptide, and protein separations. Thanks for your attention, and Jim and I will be happy to answer any questions you may have.
Thank you, Jim and Stephanie, for those informative presentations. It is now time to begin the question and answer period. So we'd just like to remind everyone in the audience that if you would like to submit a question, you can do that by typing it in the Q&A box, and you can find that on the right-hand side of your presentation window. All right, so let's get started with the questions that have been coming in. So here's one to start with. I'll start with this one for you, Stephanie.
Okay.
Is a 1.5 millimeter ID column suitable for conventional UV detector cell volume, or do we need a smaller cell volume?
Okay, yes, that's a very good question. So in all the results that I showed today, we were using a 1 microliter volume flow cell, and I would recommend that if you have a larger volume, say 2 or 5 microliters, that you would switch to a smaller volume flow cell in order to see the most that the 1.5 column can do for you. Because in fact, if most people are running gradients, and when anything post-column for gradient is really going to impact the dispersion that you see in that broadening. So if you have a 5 microliter flow cell compared to a 1, it's really going to give you a lot of improvement. If we're able to do that. Oh, go ahead.
I was just going to chime in one other thing, too. A lot of the instrument vendors now, the way the flow cells are designed in modern times, the actual full volume of the flow cell and the actual volume that adds to dispersion are two different things. So oftentimes when you read the different instrument vendors' data on their detector flow cells, look for the number that says dispersion volume or dispersion contribution, because that'll be the one that actually matters to the performance.
Excellent tip. So, Jim, with this new column, would you still see an increase in performance on an unoptimized system?
Well, I think that the detector flow cell discussion that Stephanie just talked about, kind of falls under the grand scheme of things. We think about the injection volume itself, the connections to the column and from the column to the detector. So those are all things that need to be considered as you think about that total volume. So when you talk about an optimized system, it really depends on what actual instrument model you have, because some of them do have different overall system dispersion. So really, it's what is the total variance contribution from the system relative to a given peak on the column. And so that'll also vary based on whether a peak is less retained or more retained. Obviously, as peaks are more retained on column, they have a bigger volume, so that's something to consider too, at least within an isocratic measurement. So the biggest thing to think about is what is your overall system contribution relative to the peak, and so that calculator with some of those plots that Stephanie showed during her part of the talk, that's a good way to at least make an estimate of how much is your system having an effect on your separation versus the column itself.
Excellent. Stephanie, why these 1.5 millimeter new columns versus the 1 millimeter that are already available?
Yes, we get that question a lot. So in fact, we've introduced the 1.5 millimeter ID for those people running UHPLC systems with low dispersion, because if you're trying to run a 1 millimeter, it's actually pretty difficult to get the dispersion small enough on a UHPLC system in order to really see the true performance of a 1 millimeter ID column. And also the flow rates that are needed for 1 millimeter column are quite low in order to run the optimum flow rate. So you're talking about usually 90 microliters per minute compared to 200 microliters per minute for the 1.5 millimeter ID columns. So that's why we are introducing the 1.5s for those people who really want to get some more out of their UHPLC systems, and they're limited by the dispersion that's existing there.
Excellent. Jim, what is the effect on sample loading when moving to a 1.5 millimeter ID column from a 2.1 millimeter?
So I think it depends on, are you scaling the injected sample volume, or are you maintaining it? So a lot of the discussion in the talk today focused on maintaining the injection volume. And so the thought there is that if you load the same sample volume at the same concentration, just by virtue of the fact that you're running at lower flow rates while maintaining the velocity, your actual your analyte molecules are diluted in a smaller overall peak volume, so you're going to see higher concentration. And most of the detectors that we deal with, whether they're concentration sensitive or mass sensitive, generally you can treat it as higher amount of analyte molecule reaching the detector will give you higher signal. So one thing that other people have considered with this column is scaling it. So in the same way that you're dropping the flow rate in half to maintain the velocity, oftentimes people will have similar signal by decreasing the sample volume in half. And so there, if you're sample limited and have low volume, you can inject about half and get similar performance. So those are kind of the two ways: are you maintaining the volume, or are you scaling the volume? And so it's going to depend on which way you do that. And that's really discussing in terms of isocratic. When you're dealing with gradient focusing, things before the column don't matter as much, and so really it's just going to be, is there a little bit of broadening afterwards? But again, if you put the same volume on, you're going to get higher concentration. You're going to get higher signal at your detector. Peak height and peak area are two different things. It depends on which one are you using for measurement. But again, most people quantitatively are worried about peak area, and so you will see that doubling effect with the same volume.
Excellent. Just a reminder again to the audience that if you'd like to ask a question, just type it in the Q&A box, which is on the right-hand side of the window. Another question, let's see, Stephanie, I'll send this one to you. When you compared the 1.5 millimeter ID to 2.1 millimeter, did you change the connecting tubings?
Oh, yes, that's a very good question, too. So we kept all that tubing constant in all of our comparative experiments so that the dispersion would be the same for the 1.5 and the 2.1. If we really wanted to, boost up the 1.5, we would have made the tubing even shorter and smaller ID to minimize dispersion even more. But to keep it an even level playing field, we didn't change the tubing. We kept it all the same.
Got it. I think this was also for you, Stephanie. Did you compare with your core shell columns?
Okay, so these halo columns are in fact core shell columns or superficially porous particle columns. For fused core, the superficially porous particles are known by all these terms. So all the comparative data that was in the presentation were all of our own halo particles, which are superficially porous. I hope that answers the question.
Yes, I think it does. Another question, let's see, this one will be for Stephanie also. What are the potential limitations of a smaller ID column, such as high pressure, easy to block the column, and shorter column lifetime?
Oh, sure. So just like going from a 4.6 millimeter ID column down to a 2.1, you have to keep all the same considerations in mind. So you want to make sure you're filtering your mobile phases, you're filtering your samples, you have a smaller surface area. So of course, that's going to be more likely to plug if you're not careful with how you're handling the sample. So all those things, of course, apply when you're going to a smaller ID column.
How did you get the comparison of different ID columns as for plate number, considering the extra volume outside the column itself, as stated?
Yes. So for those comparisons, we did for the 2.1 compared to the 1.5 compared to the 1, we used the same instrument for all of those. And of course, the 1 millimeter ID column is showing us lower plates because it's more susceptible to dispersion. It's actually about 4.7 times more susceptible to dispersion compared to the 1.5 millimeter ID column.
Okay. Isn't it true that smaller ID columns have lower efficiency? That's for you, Stephanie, I think.
Yes, so we have that's conventional wisdom would tell you that as you go to smaller IDs, you're not going to have the same efficiency. But in fact, we would like to dispel that myth and say that our 1.5 millimeter ID columns are able to produce comparable efficiencies to our 2.1 millimeter ID columns. You know, loaded with the same particle size and pore size stationary phases. So we're really proud of that fact, and that's something that we spend a lot of time optimizing before we introduce these, you know, for use in people's labs.
Fantastic. Well, on that note, we'll wrap up. Jim and Stephanie, again, thank you so much for your talks today and for answering all those questions.
Awesome. Thank you so much.
Thanks, Laura.
I also want to thank all of you in the audience for attending and participating in today's event. And I'd like to thank our sponsor, Advanced Materials Technology, for making today's webcast possible. We'd like to ask all of you in the audience to participate in a brief survey, and you can see that survey on the right-hand side of your screen. You'll receive an email alerting you when the webcast is available for replay. We invite you to forward that announcement to your colleagues who might have missed today's live event. We hope to see you all next time. Goodbye.